Okay, so next up we have Bill Ellsworth, and Bill said there's probably no need to introduce him because everybody knows him except for me. We haven't met in person actually. But Bill has been part of SCEC for a long time. He recently became emeritus at Stanford, where he's served on the faculty there for 8 years. And then he spent more than 4 decades at the USGS. And I want to read this one line from Bill because I think there's so much to unpack here. So Bill's research interests can be broadly defined as the study of active faults, the earthquakes they generate, and the physics of those earthquake sources. So a lot in that one sentence. And I think we'll hear about a bit of that and maybe the do's and don'ts of an observatory like the one we're considering. So take it away, Bill.
There we go. So this talk is in part for the early career people in the room. For some of you like me, we're going to be kind of rewinding some history that we lived through while waiting for the big one. And one of the points to make is that you really need to have, I think what the Germans call Sitzfleisch, to do this job. These guys, Perry Barley and Vito Gutenberg, they divided California into pieces in the 1920s. The new SCEC Center is going to put them back together, which is great. But they used the technology of the time, the state of the art, which would have been optically recording seismometers. There were geodesists who were doing triangulation from mountaintop to mountaintop to really try to understand the San Andreas system. So this is a problem we've been with for a long time while waiting for the big one. They waited their whole careers for the big one on the San Andreas, didn't get it. I don't know whether I'm going to have that same fate or not. We shall see. Okay. So moving ahead, I want to introduce you to a kind of a cautionary tale here. This is from a proposal that Jim Dietrich put together in the early 1980s to develop a fault zone observatory to catch the big one. And to the RuFZO group, this will look like a very familiar picture, right? Okay, going from Hartfield down to the end of the San Andreas and then along, and also including the San Jacinto fault in this. Jim was given the job to develop a proposal for going forward when the earthquake program was growing, to try to put together something that would be large scale, to say, can we develop an earthquake observatory that will answer fundamental science questions? So let's look at the science questions that Jim was interested in addressing. One was, he said, let's focus on the high probability segments of the fault in Southern California. And as part of that, to deploy networks to test then current hypotheses about earthquake prediction. Early 1980s, prediction was still very much in the air, okay? But he also emphasized the importance of crustal deformation. So this was a broader scale, trying to look at the large scale processes as well as the small scale processes. And quite interestingly, he also said, we need to talk about an imminent alert system. Okay, that's the part perhaps we have finally achieved with the shake alert system in California. So it was a multi-function observatory that he was proposing to look at multiple tasks. It wasn't a single narrow science goal, but really trying to look very broadly at issues, recognizing that this would need to be done over the long term. So what did he propose? So these are figures from his report, one emphasizing the importance of seismic networks. Now remember, in the early 1980s, we were working with analog telemetry, the high frequency seismometers, things much more limited than technology today. Also, to measure crustal deformation, we're really dependent upon laser geodesy between mountaintops. So these were infrequent measurements. GPS would really not even been thought of at this point. And Jim was proposing, I think, really quite innovatively developing a network of crustal deformation observatories that would be part of this network. Well, what did these consist of? They consisted of, for example, a 2-color laser, which would be moved around. That was state-of-the-art geodesy to make infrequent measurements, but also talking about borehole strain and tiltmeters as part of the process. Okay. The other thing that Jim did was that he put together his views about probabilities that we're going to catch an earthquake. And this is the table from this report. You can't read the numbers here, but basically he estimated that to catch a magnitude 7 over 30 years, he thought there was more than a 95% chance that we would do that, given what we knew about that. Well, of course, those 30 years have expired, and we're still waiting. While we were waiting, of course, there were important earthquakes that occurred elsewhere in California. We didn't catch Landers, we didn't catch Hector Mine, we didn't catch Ridgecrest, the numbers go on and on. And so that's one of the other messages that I want to leave you with is we need to think more broadly than just a few faults. We want to catch things within a finite amount of time. So moving ahead from this, the idea that we needed to better understand the probabilities of earthquakes led to the formation of the Working Group on California Earthquake Probabilities. The first group met during 1987, released their report in 1988, and it was really focused on trying to identify where magnitude 7s would occur on San Andreas and San Jacinto Fault alone. These are figures from that report. They're a little hard to see here. The height of the bars here represent the probabilities. The numbers have changed over the years as probability reports have changed, but they haven't really changed a lot. What's important about these, I think, is that we can test these models. And this is something that the late David Jackson did in his 2019 paper. After the 30 years on this forecast had expired, one could go back and look at it. How did we do? If we had focused simply on the San Andreas during this period of time, we know what the answer would be. But David pointed out that just one earthquake from that report satisfied the criteria very clearly in a strict sense, and that was the 2004 Parkfield earthquake. Wasn't magnitude 7, but it was one that was included. So it's been interesting to me to hear that Elise first and then Anne-Marie, they both mentioned Parkfield. So you're going to hear more about Parkfield as we move along here. The other thing that David noted was that Loma Prieta was kind of marginal. It may have fit, it may not have fit the model. If you included it, that it did in fact pass the N test, the CSEP N test at the 5% quantile score. And Parkfield alone was enough to pass the S test. So the message here was that the 1988 report passes, but just marginally. Again, it's too narrow in focus. I think that's really the thing that we have learned. So let's take a little bbit deeper dive into Parkfield, which you've heard something about already. For those of you who don't know the history, I'm going to back up here just a little bit. Parkfield had been identified much earlier, in certainly my career, as a place where it was going to be important to capture earthquakes. The early strong motion seismologists in California knew that. They seeded the ground and caught the 1966 earthquake. So there was some idea that it was important to go to places where earthquakes had happened in the past. We would have a chance to catch them. Same thing in the Imperial Valley and other places around California. But in the mid-1980s, there was the thought that if we were going to move forward, we needed to lay a trap to catch some earthquakes. This seemed like a good place to go. And in about 1985, the California Geological Survey came to the USGS and said, we'd like to partner with you to enhance what we're doing at Parkfield. And so that was really the beginning of the Parkfield experiment. There were a couple of years that were involved in setting the traps and then putting them in the ground. So let's look at what was done. This is the network. There are lots of colors here on the map, lots of dots, and it's a long list of things. There are creep meters, there was geodesy, eventually there was continuous GPS, there are dilatometers, there are tensor strain meters, water wells were being measured, there's weak motion, strong motion, dense arrays of seismometers, etc. Magnetometers, resistivity, many things were being measured with 3 specific goals, one of which was to observe the buildup and release of stress on the San Andreas through multiple earthquake cycles. The second was to test the feasibility of short-term prediction. This is the one that probably has gotten the most attention. And then the third was to measure the shaking during earthquakes. It's really an opportunity to capture this in much greater detail than had happened before. And of course, we had to wait a while for the earthquake, but it did eventually occur in 2004 and really yielded a remarkable collection of data that we've already heard referenced. The figure on the left here shows the strong motion data, colored here by the amplitudes. And just a few highlights from that. This first panel here shows the peak acceleration versus distance from the fault. The lines here represent a particular ground motion model. And what was, I think, quite surprising about the results from Parkfield was that the data from Parkfield spanned the range of what was thought was going to be the proper range. So it was clear that the models needed to be revised. There was more variability than we were taking account of. The middle panel here is from Jessica Murray's work, looking at the long-term cycles. And one of the things that was discovered after 2004 was that these Parkfield earthquakes were not clearing out all of the accumulated displacement. Displacement was still building up, despite the fact that we were getting a magnitude 6 every 25 years. And finally, even with all of these data, we're just now beginning to converge on what the rupture model was. So I was very interested in this new work that Elise was showing that may be beginning to get at the issue as to whether we have a skinny rupture that was confined in some way that's being controlled by material properties. So the other thing that we learned about Parkfield was that prediction is going to be really difficult, if perhaps not impossible. And we had the observations that allowed us to say that there were no foreshocks. That was an easy one. Thanks to the deployment of tensor strain meters, dilatometers, and other strain sensitive instruments, we could say there was no accelerating deformation going into the time of the earthquake. And that's down to a scale of about 1/100th of a second. And then finally, we can say that there were also no things such as magnetic field changes and other things. They just simply did not happen. So it's a negative result, but it was one that was well defined by the experiment. So moving forward, we now have a much richer view of what we think the probabilities of earthquakes are going to be, not only on the San Andreas, but across California. This is from the USERTH 3 report. And you can see that there are many, many faults here, in addition to the big one that we think about, that are really ripe for monitoring. So I was really encouraged by Yehuda's comments that already we're thinking about going beyond just Southern California in terms of this. I think that's going to be a really important thing to do. So where might we go? Well, it depends on what we want to learn, but an obvious place to make sure that we continue to sit is Parkfield. Okay, this is a figure that I put together in 1999, in which I was comparing then available earthquake forecasts for Parkfield, all in the literature, giving the probability, the annual probability of an earthquake as times through the cycle. So that the axis here starts with the 1966 earthquake running through time here. Of course, the earthquake eventually occurred in 2004. There's some models that really you can rule out. They were just too improbable. And probably that's true at the bottom end as well. But there are many models that were still within the right range. The probability of the earthquake happening when it did in 2004 was really set, is consistent with these models. Well, if we think of this Parkfield as an independent, identical independent random process, we can just rescale the axis here and start counting in again from 2004. So we're in 2023. We're getting into the area where the probability is not small. It may still be a good place to be sitting if we can formulate the questions that we want to answer by sitting there. So let me change gears here for just a minute. I'm going to take you to Turkey. And the reason I want to do that is that this is perhaps the best recorded continental strike slip earthquake ever. And I think we can learn a lot from what was seen in this earthquake as we think about the best way to proceed with monitoring in California. They laid out a really remarkable track. The little, perhaps you can see the little red triangles here represent strong motion stations that were installed that are within just a few kilometers of the fault, some actually within a few hundred meters. This is the wave field from the main shock. It has sort of two pieces. The lower piece here represents the progenitor event, the initiator event, which began here and then ruptured on this small fault before it hit the main fault, and as I think many of you know, branched and before it ran down along these lines. And then you can see, of course, the waves from the main fault, the main rupture as it's running by this picket line of the station. So if we want to know the rupture velocity, get a ruler. Okay, it's really quite obvious, isn't it? So main ruptures running at about an average of about 2.85 kilometers per second. Okay, so this is great. So with all of these data, it turns out there's only one place where they had two instruments that saw the same part of the fault. So let's take a look at that. And that's on the initiator fault here. It's two stations at this location. So it's about 20 kilometers from the epicenter. And it's over about a 12-kilometer segment, which is the only part that ruptured the surface during that initiation event. And after that, it then propagates another 10 kilometers roughly before it hits the main fault. Okay, so this is the setup. We're looking here at the two stations. One is located about 600 meters from the fault, the other about 900 meters. Displacements are on the order of kind of 2 to 3 meters through here. The photograph at this position is looking along the rail line. And I think you can very clearly see that this is a left lateral fault. There's about 2 meters of displacement at this location. There are actually two traces. There's one here, one here. And I think you can also see that there is a down to the north component as well. Okay. So those are the pieces we have to work with. And we've got the opportunity now to see actually what happened, because both of these stations really allowed us to recover the absolute displacements. So at the station that is to the east, called NAR, again about 600 meters from the fault, these are the integrated accelegrams all the way to displacement. We're interested in the white part. The gray part here represents the waves from the rupture of the main fault that comes in later. And I think you can see that in this one, the up-down component indicates very little vertical offset. It's moving kind of in a direction which is at 45 degrees to the fault, both the fault parallel and fault normal. Total displacement is kind of on the order of about 1 meter. And the down motion is perhaps 5 centimeters. I don't think it's more than that. On the other side, we're looking at a station that's 900 meters away, and it's got a very, very different pattern. It is almost entirely into the horizontal displacement is pretty much fault parallel, and it dropped by about 70 centimeters. Okay, well, that is really not very elastic behavior. So it's really quite interesting that there are things going on that we're going to be confronted with if we sit near the fault that are inelastic. And one question, what types of data do we need to capture that? Is this seismometers alone? What are the other things that we really need, that we must have if we're going to address these problems? Here we go. So coming back to California, I took a quick look through some of the old IRIS tools as to where we have stations in California to try to see where we might have some gaps. And actually, the seismic network is pretty amazing. These are broadband and strong motion stations across the state. If you go up and down the state, it was hard to find any place where we had a 10-kilometer gap in strong motion coverage along the main trace of the San Andreas, one end to the other. So we've really done a good job with that. And I think in many ways we have the early warning system to thank for that. That's important because that's the system that we're going to run. As Maggie reminded us, NSF doesn't provide batteries when they provide instruments. So we have to figure out ways about keeping these things running in the long term. Also, GPS is really something that's really accelerated. So we're doing a very good job in terms of broad scale. And the question is, what do we need to do to augment these to take advantage, to move things forward? One thing I think that we need to think about is what are the new technologies that we need to use? From Jim Dietrich's work way back, 40 years ago now, none of the things that Jim was thinking about, we'd even think about deploying today, right? What are where is the cutting edge? Where do we need to be moving forward in terms of really the most modern, the most capable system that we might deploy. Gas is an obvious one. And so that's one to think about. I think the other is to think about going to depth. It's expensive, but we have to think about it. This is from a figure from the kind of the original proposal to drill into the San Andreas from the 1998 proposal. As far as we got was the pilot hole experiment here. If we want to go deeper, we really have to think about that. So I want to close here with just a few thoughts about where I think we should be heading. One is that capturing events of sufficient magnitude to answer these key science questions are going to require instrumenting multiple faults. We're a statewide center. I think we need to think about more faults than just the San Andreas. We want to make sure that we don't get surprised by the next Landers or the next Ridgecrest, you name the earthquake. Second is that this is patience. This is going to take years, if not decades, to achieve. I think our history tells us as much. We might get lucky and catch one sooner, but we have to think about how this is going to be paid for in the long haul. And I think that was the other message that Maggie was delivering to us. It's going to take more than one agency. State of California may be one that would be interested in being as part of this in the long term. USGS, perhaps others as well. And with that, I'm going to stop and see if we have any questions. So thank you.
Yeah, I really appreciate the suggestion of going back to Parkfield, because that's something we're going to discuss in the section after this. It's important to expand beyond our initial regional focus. Questions? I'm sure there's some questions.
Bill, has there been any INSAR work to kind of shed some light on these very conflicting or very different observations on the two sides of the?
Yeah, that's a really good question. I don't know the status of that, but that's an obvious thing to be looking at. It's also worth thinking about in say California. Are there things that we should be doing before? Like, so we have the B4 surveys, the LiDAR surveys along the San Andreas. Those are the important things to be maintaining. But as technology changes, we should be keeping with that as well. UAVs are other methods as well. Good point. Yeah.
San Bernardino County, we employ the INSAR for fault location, and we've done zonation, and it's already accommodated in the county's emergency mitigation plan, and that was accepted by BEAM.
That's great. Yeah, Ramon.
Yeah, thanks for the attention on Parkfield, also one of my favorite places. And, you know, after the 2004 earthquake, we were out there with USGS colleagues, and the lesson was the value in observing the surface rupture itself and its evolution. So, you know, within a couple of days, we focused and mapped the fractures, and it was done quite manually. So it was just a few hundred meters really of detail. And then the missed opportunity was that it continued to evolve. So the sort of growth of the and linkage of the fault at the surface was really not captured at all. You know, we were there 3 days after and then went back to teach classes, and it continued to grow. People talked anecdotally, and then it rained after 3 weeks, and it was completely kind of really significantly erased. So I think one thing as far as an opportunity beyond some of the technological and geodetic observations that might observe at depth is the evolution of the surface rupture, and that might include kind of robotic observations of UAS in the near field, and really being able to be there quite quickly, and then and I think in some of the early RuFZOs we talked about some really shallow geophysics that might characterize more like kind of environmental geophysics type applications, shallow magnetics, resistivity, some seismology, to look at the evolving kind of mechanical properties of that upper few hundred meters of the volume at really high resolution, kind of the decameter scale, and so it's quite challenging to make such detailed observations over large distances. So some kind of hierarchical design will probably be required as well.
Yeah, that's a good point. And just for those of you who don't know, at day 0, there was no surface rupture at Parkfield. So it was really all afterslip that came to the surface. So a question might be, are there ways that we might actually capture how the fault ruptures at some of these sites, you know, through photography or whatever?
Yeah.
Yeah.
Yeah, I just had a question really about how to define sufficient here. So I'm just curious, like, what are the priorities for this observatory? Because are we trying to set a trap and catch the big one, or are we counting more moderate and smaller magnitude events? Because there seems to be a rich amount of science there too.
Yeah. I'm gonna
So what are the
let Yehuda answer that question.
No, but I mean, okay, so in my slide, there are many goals, including using the small ones. And if we are lucky enough, if you want to look at it like that, we will also capture a big one, but we can achieve a lot, and we need this information before we get the big one. I just want to take the point, since I'm speaking now, first, thank you for the great talk. And of course, as you pointed out, something inelastic occurs in the fault zone. It's not elastic by definition. And these inelastic processes hold the key to improve our understanding of and getting more predictive model for both earthquake physics and ground motion. So it's an unexplored territory. And again, it is not elastic, of course.
And I would add to that the important part is not in the upper 100 meters of the surface. The other part that we try to look through, we really should be thinking about how we make observations of depth. And, you know, perhaps with technologies like DAS, we have the opportunity to do more of that in the near source region.
Maybe one more question. Yeah.
You talked about like putting instruments on different faults that are outside of Parkfield, you know, and you're focusing on a lot of these normalizations. And it makes me think of other faults that are along the line of San Andreas, like the Calaveras or Hayward, Garlock, or something like that. But do you have some suggestions of other places that you can focus these tracks on?
Well, again, you know, I think we have to look at a little bit of our history with a little bit of hubris. And, you know, we think about Landers and Hector Mine and Ridgecrest and Petrolia, and you know the list goes on and on of places that are off the main fault that have been active. So I think thinking about how we set traps with specific science goals is going to be important. And we're not going to hit them all, but if we don't try, we aren't going to hit any of them. I think that's the way I look at it.